This presentation is my attempt to explain the band structure, including what is the band structure, where do the bands come from, and what feature is important in the band structure. Before I'm starting the talk, I highly recommend this book by Hoffmann called Solid and Surfaces. If there are concepts that was unclear during my presentation, or if I'm going too fast, at some point I highly recommend you guys to read the first couple chapters of this book, which I think Hoffmann did a really good job at explaining these concepts in concise detail. To understand the band structure, let's start with a single hydrogen atom with one atomic orbital, the 1s orbital. Now let's say we have two hydrogen atoms, then we will have two atomic orbitals, both have the same energy. If we force these two hydrogen atoms to form a bond, the two atomic orbitals will now combine to form two molecular orbitals, a bonding and an anti-bonding orbitals. If you guys are not familiar with molecular orbital theory, there are a ton of resources online. I recommend to go read about them first before continue watch this video, because this is one of the key concepts to help you understand the band structure. As I mentioned on the previous slide, two hydrogen atoms in the hydrogen molecule will form a bonding and an anti-bonding orbital. The bonding orbital of course have the lower energy. Notice that the two 1s orbitals are in phase with one another for the bonding case, and in the anti-bonding case the two orbitals are out of phase with one another. There's a nodal plane in between the two 1s orbital in the anti-bonding case. Another concept to notice here is that if we increase the number of nodes, we will increase the energy of the molecular orbital. Let's increase the number of hydrogen atoms to 3 now. We apply the same concept as before. We had 3 atomic orbitals, so we should have 3 molecular orbitals. The lowest energy orbital will have the 3 1s orbital in phase with one another, and the highest energy molecular orbital will have the larger amount of node, 2 in this case, and the intermediate one will have 1 node, as shown in this figure right here. Let's do one more of these, adding one more hydrogen atom into the chain. Now we're gonna have 4 molecular orbitals, lowest one with 0 node, highest one with 3 nodes, and those in between with 1 and 2 nodes accordingly. What if instead of having these small number of atoms, we increase the number of hydrogen atoms in our chain to 14? We can see that the same concept can be applied here. Lowest molecular orbital with 0 node and the highest molecular orbital with 13 nodes. And since we have 14 molecular orbitals, there will be 12 molecular orbitals in between those highest and lowest energy molecular orbital. Let's make this more complicated. Let's say we have an infinite amount of hydrogen atoms in a chain. We will have an infinite number of molecular orbitals in between the lowest and the highest energy molecular orbital. It is kind of impossible to model these at discrete energy level now. So instead of drawing infinite line in between these molecular orbitals, we model them as band of energy instead. Now we have a band of energy, but how are we going to describe or distinguish the orbitals within this band? There must be a way to specify which energy level corresponds to which orbital within the band, and how many nodes are associated with a specific orbital. This is where the Bloch function comes into place, and the Bloch function is a solution to the Schrödinger equation in the form of a plain way to describe the electron in a periodic potential. If you want to read more about the Bloch function, you're welcome to look it up. There's a ton of information that you can find online. Here I label my chain of hydrogen atom with index n. A is the distance between the hydrogen atom. Chi represents the basic function for each 1s orbital. I is the imaginary number. K is the index, or in this case a wave number for this periodic function. And since we are dealing with a chain of hydrogen atom, this is one-dimensional problem. So I'm just picking x as a direction that the chain is orientated in. Notice that it can also be y or z, whichever you choose. So now let's say that we are assigning the value of k equal to 0. Then the Bloch function will give us this result, where we have plus 1 as a coefficient in front of all of our basis function correspond to all of the 1s orbital or in phase with one another. If you remember back to the example that I gave before, this plane wave should correspond to the lowest energy orbitals. What if we set k equal to pi over a? In that case, similarly, we will apply the math. We see that for all basis function with the even index, we will have a coefficient of plus 1 in front of the basic function, and for those with the odd index, we will have a coefficient of negative 1 in front of them. This corresponds to the case where we have all adjacent 1s orbital are not in phase with one another. Hence, we have the maximum amount of node, and this corresponds to the highest energy orbital. Intuitively, when we increase k from 0 to pi over a, we will increase the number of nodes, hence we are increasing the energy of the orbitals. However, if k is smaller than 0 or larger than pi over a, we do not get a new wave function, but an old one that is similar to those in the range between 0 to pi over a. This is what we call the first Brillouin zone, the range of unique k. Now we have a way to represent the energy of those molecular orbitals as band and how to distinguish between these orbitals using k. We can use them to understand the electronic property of the material. However, so far we have a case of a hydrogen change, and we only have one atomic orbital to deal with, hence we only have one band. But what if we have more than one band, let's say 2? If their energy are very far off from one another, we can still represent them as a rectangular block like this, and it's still reasonable to look at. Now let's say we have 3 bands and their energy kind of overlap. We still have a reasonable figure to visualize our band structure. But let's say we have more than 3 bands, we have 10, then we will have this. And pretty soon, as the number of bands increases, this will get very complicated to read very quickly. So let's get rid of this representation and try to use another method. As I said before, the bands are made up of very closely packed discrete molecular orbitals. So let's pretend the red line through right here represents those energy levels. Now we can turn this one-dimensional representation of the band to a two-dimensional representation. Now we have k on the horizontal axis and energy on the vertical axis. However, do we really want to draw these bands into the representation like this? It will also make things very messy very soon when we add more band into it. So instead of drawing each orbital as a line, we can just represent them as points on the graph. So imagine that you're cutting a slice of the band and put them into a 2D representation that we have on the previous slide. Is another way to think about it. Now this is what we get, a curve of energy as a function of the wave number k. This right here is what we call the band structure. And since this is the one-dimensional chain, as we are assembling k in that direction, we're changing the phasing of the orbital in that one x direction, which gives rise to the different energy level, hence the emergence of the band. Let's go back to our example of the chain of hydrogen atoms. In this case, k is an index in the block function that corresponds to the changes in the phasing of the orbitals in the x direction, which I choose again. I could choose y or z in the beginning if I want to. What if instead of having a 1D chain, we have a sheet of hydrogen atoms? Now k no longer is a single index, but k is a vector that contains information about the phasing of these orbitals in both the x and the y direction, which I show here as kx and ky in the equation. Similarly, if we have a 3D materials, we need to include in our k vector a component in the z direction that can describe the change in phasing of the orbitals in this direction, and I name it here as kz. For simplicity, I will talk about the 2D case only in this video, but it's very simple to apply this concept to the 3D case if you understand the 2D case very well. If we have a 2D sheet, our first Brillouin zone will be different now since we have to account for both the x and the y direction. So instead of having a line as the first Brillouin zone, we will have a square instead. To make it more simple, people provided name for these k vector, each of which represent a high symmetry point. For example, gamma represents the origin in the first Brillouin zone, where kx, ky, and kz equal to 0. This represents a case where all of the 1s orbital in our hydrogen sheet are in phase with one another, lowest energy molecular orbital in this case. Similarly, we can assign other point with different symbol. However, since our first Brillouin zone is a square now, we need to take symmetry into account. If we have either kx or ky equal to pi over a and the other equal to 0, show as capital X on the picture over here. In this highly symmetric material, we have two k vectors that represent the exact same facing, just different direction. And if you look at the facing of the orbital of the two x vector, they have similar number of nodes and similar energy. This is something we want to watch out for as we are modeling a material and want to capture the band structure. We want to assemble between important k vector that could capture all different energy level that this molecular orbital can adapt. Changing kx, ky, and kz alone one at a time cannot help us capture all the possible energy that the molecular orbital can have. Let's continue to talk about the last symmetry point that I label on here, M, which representing the case where all adjacent 1s orbital are out phase with one another. So as expected, M corresponds to the orbital with the highest energy. If we're going to draw out the band structure for the 2D sheet, we will see that the energy at M would be the highest, the energy at gamma would be the lowest, and the energy at X would be in between gamma and M. This is the band structure for this material that I took out from the Hoffmann book, and it matched with our prediction. This is the case where we have a 2D material, but if we increase this scenario to a 3D material, we can apply the same concept as discussed here, and we just need to include an account for the Jangen facing in the Z direction. Now that we understand the band structure, I want to talk about the two most important features that we should look at when we look at the band structure. The first one is band dispersion, also known as bandwidth. And the band dispersion tells you the range of energy that electrons are allowed to occupy. To understand what gives rise to band dispersion, I want to bring back the example of the hydrogen molecule. As you are shortening the bond between these two hydrogen atoms, you see the destabilization of the anti-bonding orbital as shown right here, and the stabilization of the bonding orbital, which widen the gap between these two molecular orbitals. Imagine instead of having these two discrete molecular orbitals, you're going to have a band of energy. So as you are compressing the hydrogen chain, you're going to see the destabilization of the highest energy orbital and the stabilization of the lowest energy orbital. So the band gonna get longer, or in this case, get more dispersed. What gives rise to band dispersion is the overlapping of the interacting orbital. The more overlap you have, the more dispersed your band gonna be. The other important feature in the band structure is the band gap. The gap between the highest occupied molecular orbital, also known as the valence band, and the lowest unoccupied molecular orbital, also known as the conduction band. This gap in the band structure will tell us if the material is a metal, a semiconductor, or an insulator, which is important in characterizing the material for various applications. If you want more information about band gap, feel free to look up resources online. There are tons of good websites that explain this in good detail. In summary, here are some concepts that I think is important in trying to understand a band structure. A band structure is a 2D representation of the electronic property of the material in the form of E versus K, where K is a vector containing point in the Brillouin zone. There are as many bands as there are orbitals in a unit cell. Band dispersion depends on the overlap between the interacting orbitals. And the key takeaway that I think is the most important to me is that the K vector in the Brilliant zone is really different from point in real translational space. K represents the facing of the orbital in a direction that corresponds to a direction in the real space, not point in real space. And that's what I want you to take away from my presentation.